Okay, this is the video segment of tonight's homework 829. If you're in my regular Math 1 classes, I want you to copy all this work and write down the 5 words to show me you listened from beginning to end and turn that work in. For my honors classes, you're going to be doing this work and you're going to be documenting this work on your Google Slides. I'd like you to make a quick video explaining the geometric sequence 1, and then I want you to work on that quick little Flipgrid assignment where either you're showing your face or not, explaining me some main differences between these two types of sequences. So here we go, the work part. I'd like you to write this table down, 15, 18, 21. I hope that you see that these are going up by 3, all of them. So that means it's arithmetic and adding 1. I could tell they're all adding 3. If you go backwards a step, minus 3, you get 12. Those are everything I need. That is my 0 term, my f of 1 term, and my common difference d. So if I wanted to write the recursive form, I replace that d with the number that I'm adding each time. That is the equation in recursive form. And of course, to use it, to find any term in the sequence, use the 1 before it and keep adding 3. To show the work for it, I plug in 4. 4 for x gives me 4 minus 1 plus 3. Gives me the function at the third term plus 3. Of course, the function at the third term is the number right before the fourth one you're trying to find. So I replace that with the numerical value 21, and I add that 3, which gives me the function at the fourth term is, of course, 24. The first word is let's. Let's. So keep continuing that pattern, adding 3, 24, adding 3, 27, adding 3, 30. Notice skipping from 6 to 51, I want you to recognize you have to use the equation now. So the equation with the common difference number plugged in for d is 3x plus the f0 term right here, 0, 12. When x is plugged into the function, f of x is 12. So that gives me 12 right there. That's the equation I'm going to use. To find the 51st term, I'm going to plug in 51 right here. Equals 3 times 51 plus that 12. Of course, multiply before you add, so 3 times 51 gives me 153 plus 12. And then when I add those up, the function at the 51st term, or after 51 hours, just adding 3 little ants at a time, gives me 165. Constant rate of change, adding by 3 every time. If I want to shift over and use the f of 1 term instead, I use that same 3 and then that x minus 1 plus, and now I replace that f of 1 with what the value really is at the first term. Or when I plug in 1, I get 15. So that is the f of 1 term right there. And then if I was to use that, I would plug in 51 right here for x. I would leave that 3 alone and plug in the other 51 right here and subtract 1 plus that 15 from the first term. That gives me 3 times in parentheses 50 plus 15. And of course that gives me 150 plus 15. Which gives me 165, the same amount. You got to know that these are equivalent. These both give you the same answer. If I was to distribute this in this form, 3 times x, 3 times negative 1, that negative 3 I get from this part of the distribute, combined with that 15, gives me the same equation, 3x plus 12, because negative 3 and 15 is 12. So hopefully you see those are equivalent. The second word is go. Go. All right, the next problem is geometric. So for this one, write these numbers in. 3, 6, 12. I want you to see that these are not just going up by 3. This is going up by 3. This is going up by 6. I want you to see that. These are timesing ones. 3 times 2, 6 times 2, which means to the left is dividing by 2, but we show division as multiplying by the reciprocal of 2. So flip-flopping 2 into 1/2, that's the same as dividing by 2, timesing by a half. To show how I take that 3 and times by a half, again, 3 is a whole number over 1. 3 times 1 is 3. 2 times 1 is 2. That ends up being 3 halves. 3 over 2. If I was to extend it further, this next term to the left, -1, would be 3 halves times another half, would be 3 times 1 over 2, would be 3/4. And if I time that 3/4 times another half, would end up being 3/8. We'll be talking about that. All right, but for this, just go to the 0 term. The recursive form is f of x equals f of x minus 1 times that common ratio number, which is 2. Of course, the recursive pattern is to find this next term, take 12 times 2, 24. To find this next term, take 24 times 2, 48. But to show the work in the recursive form, plug in 4 right here and 4 right here for x times 2. That gives me the function at the third term times 2. I replace that f of 3 with the value at the third term, which is 12 times 2, which tells me that the math to find the fourth term using this recursive function is the number before it, 12 times 2, which gives you 24. I want you to fill in the rest using the recursive pattern. 24. 24 times 2, 48. 48 times 2, 96. But can't go any further. And remember, going to the left, dividing by 2 or timesing by a half. 96 times a half is 48. Times 1/2 divides it by 2 is 24. Times 1/2 divides it by 2 is 12. If I use the formula to find the 12th term, I use the f of 0 term, which is 3 halves, and put that 3 halves in for the f of 0 term. The 0 term, or when x is 0, plugged into this function is 3 halves, times that number I'm multiplying. This is the common ratio r, 2 raised to the x power. The third word is Liverpool, Liverpool. To find the 12th term, I'm plugging in 12 right here for x. I'm leaving that 3 halves alone. And for that 2, leaving that alone. But where that x is, that's where the 12 is being plugged in there. Order of operations says do this exponent before you times by 3 halves. So using my calculator to raise 2 to the 12th power, never 2 times 12, never multiply a base times a power. That's 12 2's listed out times in each other. Using my calculator will multiply 12 2's in a row in a millisecond. Gives me 4,096. 12 of those 2's times each other. To do this problem, I could do what's called cross cancel if I want, which means divide this number by 2, which is 1. Divide this number by 2, which is 2,048. And then all I have to do right there is just multiply 3 times 2,048. Or, if I don't want to cross cancel and just multiply what I got left after that, I could just leave it alone and put that 4,096 over 1 and just times straight across. 3 times 4,096, I believe, is 12,288. 2 times 1 is 2. When I divide that out, I get the 12th term is, using my calculator, 6,144. And that number would go right here, or if it's too big, you can write it out and draw a little arrow in there. If I want to shift over and use the first term instead, that would be f of x equals, and then the first term here, I'm using 3. So you could see no fraction there, which some people like, but you got this weird x minus 1 here to remember. So 3 times that common ratio number, which is 2, raised to the x minus 1 power. This will give you the same answer. When I plug that in, the fourth word is beat. Beat. When I plug that in, f of 12 equals 3 times 2, and I put a 12 right here, 12 minus 1. That gives me 3 times 2 to the 11th power. Never times this 3 and 2 first to get 6. Never. Do 2 to the 11th first. 2 11 times listed out. Calculator does it quick. Never times 2 times 11 to get 22. Never. 2 times 2 times 2, 11 times, 2,048. And then that times 3 gives me that same answer. The function at the 12th term is 6,144. Okay, for these sequences, a couple other things I want you to remember. I want you to know that as if I was to graph these with x on the x-axis and the y-axis now being called f of x, these are your x numbers. These are your y numbers, or your f of x numbers. These would curve up sharply, just like that. Start off kind of small. You can see if I go back right there. Let's see, sorry about that. You can see when you graph these and looking at that table, the numbers start off small, 3 halves, 3, 6, and then start getting bigger and bigger. Let's shoot up to 6,000. But if you look at arithmetic graphs, with x on the x-axis and the y-axis called f of x-axis now. This one has a y-intercept of 0, 12, so it's not proportional. It'll be up here on the y-axis. Would be a straight line, always constant rate of change. I'm adding 3 every single time, going up by 3 every time. Over 1 up 3, over 1 up 3, over 1 up 3, over 1 for x, up 3, over 1 up next day, up 3 more ants. Exponentials are the opposite. Exponentials do not have a constant rate of change. This amount going up by each time, even though you're timesing by 2, it's not the same. Up by 3, it's up by 6, it's up by 12. No constant rate of change. That's what makes those graphs curve up. The last word is city. City. Good luck. My Math 1 students, take documentation of that, like I said, video the geometric one, and then follow the directions on the flip grid. Good luck.